Hi everyone. Today we're going to be talking about the rates of change of an area. This is a nice way to link some things that we did last term with some things that we're doing this term. Right? This term's been all about finding the area under a curve, and so now what we'll do is we'll find the rate of change of that to bring in some topics from last term. So hopefully you recall from last term that the rate of change is the derivative. So if we have some old function here, right, and it's got some area on this interval from a to b, what we're going to imagine is, what if we went a little bit further rather than stopping at b? What would this change in area be as we increased our area slightly? And so what I'm going to do is, rather than call the upper bound b some fixed value, I'm going to call it x, some value that can change, right? This is our variable. And so to find the rate of change of the area, well, the area itself is the integral from a to x. Well, I can't call this f of x anymore because I've used x as my upper bound. So I'll call this I'll just make up a new variable, f of t. This is a function, and this particular function, it changes what the upper bound is. It's a function of x. So to find the rate of change, I'll just take the derivative with respect to x. Now we should recall from way back when in September how to take a derivative. Even if we don't have any particular rule for it, we'll remember that derivative just means instantaneous rate of change. Any old rate of change is just the change in y over the change in x. And so we recall the definition of a derivative, which is the limit as h goes to 0 of f of x plus h minus f of x all over h. And in this case, x is there, so it becomes the integral from a to x plus h of f of t minus the integral from a to x of f of t all over h. And let's tidy this up a little bit. We know some properties of integrals, which is really cool. This is the integral from a all the way up to x plus h. So that's the area under the curve from a all the way until x plus h. And then we're taking away the area from a all the way up to x. So what we're left with is just the area from x to x plus h. Right? This is the whole area. Then we're taking away the area all the way up to x. So we should just be left with the integral from x to x plus h of f of t dt. And I'm just going to tidy this up as well. Rather than leaving this all over h, I'm actually going to write 1 over h out in front. And you might think to yourself, well, that's dumb. Now I have a fraction times a thing rather than just one fraction. And you're right, it is kind of dumb. But the reason that I'll write it this way is because we've seen something that looks just like this in our last section. You may notice that if I'm from x to x plus h, the width of my entire interval is just h. That's right, sneakily in disguise, this is the mean value theorem, right? Which says that if I have this nice function and it's integrable on the whole interval, then there exists some c in that interval where there is f of c is the average value of the function. And the average value of the function is this. So that means I can just rewrite this as f of c, where c is in the interval. I don't know what c is, but that's okay. It's just some value in that interval. And here comes the real exciting part. If c is between x and x plus h, but h is going to 0, c is getting trapped. C has no choice. C is heading towards x. This has to be f of x. And that should be crazy. You should look at this and be like screaming and yelling and going off and showing your friends out in the hallway how awesome this fact is, right? If I take the derivative of an integral, I get back the original function. That is so cool. In fact, it's so powerful that this is the foundation of all of calculus. This is the link between integral calculus and differential calculus. And aptly, this is named the fundamental theorem of calculus. So let me just erase this and rewrite the fundamental theorem of calculus in a nice way so that we can use it for some example problems here. So let's see. I have the derivative of an integral of a function is that original function. So cool, so awesome. I know. Great. So let's do an example. Let's say I wanted to find the derivative of the integral from 0 to x of cosine of t dt. Well, the fundamental theorem of calculus says that's just this function of x. This is just cosine of x. Crazy, right? Similarly, I could take the derivative of really anything I want, maybe 0 to x of square root 1 plus x. Oops, I always write x there. It should be t. Well, again, this is just the square root of 1 plus x squared. The next example is going to be a little bit trickier, but it'll still work out just the same. Let's say we had the derivative, but instead of going from 0 to x, we went from 0 all the way up to x squared. 1 plus t dt. Rather than this being a function of x, as these ones were, this is now a function of x squared. That means we have some inside function here. Our inside function is x squared. So when we take the derivative, whenever you take a derivative and there's an inside function, you have to remember to end by multiplying the derivative of that inside function. This, we replace the t with our upper bound, just like we've done in the past, but then we have to remember to multiply by the derivative of the inside function, which is x squared, and that's derivative is 2x. Here comes our last example. Let's say we start out with the fundamental theorem of calculus. If the derivative of this integral is this function, I can take the antiderivative of both sides here and see something pretty cool. The integral from 0 to x of f of t dt has to be the antiderivative of f, okay, plus some constant. That would give me all possible values here, right? This has to be f of x plus c. I don't know what the c is, but that's okay. Now, you might have been thinking this whole time, this is really dumb. Why do I want to change where the area ends? Maybe instead you don't. Maybe you just want to go from A to B. Because usually, if we're dealing with finding an area, we're finding the area of something that already exists, something that is bounded. So notice that f of b plus c has to be the integral from a to b of f of t dt. F of a plus c has to be the integral from a to a of f of t dt. These are kind of cool facts, but I can put them all together in this really, really nifty way right here. If I subtract these two equations, on the left-hand side I get f of b minus f of a. On the right-hand side, this is super cool. Ready? I get the integral of f of t from a to b. The integral from a to a of f of t is just 0. It's just 0, and it's always 0 because I'm finding the area over an interval whose width is 0. By doing this, I've eliminated the need for these constants here. And in fact, I can evaluate this integral directly. I can find any area I want using antiderivatives. This is so awesome, right? Any shape you draw, any at all, I can find the area underneath it by using the antiderivative. This is so powerful. This is the most powerful statement that you will see in this course. Okay? The fundamental theorem of calculus, which leads directly to a corollary of the fundamental theorem of calculus that is so strong we sometimes call it the fundamental theorem of calculus, part 2. So let me write this new result up here, and we can do some examples with it as well. And in fact, the examples that we'll do are examples that we've done before, and we'll show that these answers match the same answers we got before. So, we'll recall the fundamental theorem of calculus, part 2. The integral from a to b of some function, and now I can call it f of x, because I'm not using x up there, is just f of b minus f of a. Great. Super powerful. So, let's look at some examples. We saw this example last time. We looked at the integral from 2 to 4 of x cubed plus 2x minus 3 dx. And before, I didn't know how to do this, and I just used fnint on my calculator. But now, I'm going to change it up. I'm going to actually just evaluate it. So let's see what I get. Well, I'll take the antiderivative first. The antiderivative of this is 1/4 x to the 4th plus x squared minus 3x. And again, I get that plus c, but I don't have to worry about that anymore, because remember, when I subtract these bounds, that disappears. So I'm not even going to bother writing the plus c. What I will do, and this is some new notation, is I need to somehow indicate that these bounds are still important. The integral sign is gone because I've taken the integral, I've taken the antiderivative, but I'm going from 2 to 4. So at the end, I'll put this vertical line with a 2 and a 4. Great. And then I'll just evaluate it. I plug in 4 for all of my x's. 4 to the 4th is 256. Divided by 4 is 64. This is 64. 4 squared is 16. 3 times 4 is 12. So that's my f of b here. I'll subtract from it. I'll plug in 2 here. 2 to the 4th is 16. Divided by 4 is 4. 2 squared is 4. 3 times 2 is 6. And let's see what I get out. 64 plus 16 is 80. Minus 12 is 68. Minus, that's 2. 68 minus 2 is 66. Hey, you should recall that when we did fnint on our calculator, we got 66. That's awesome. Now we can do it by hand. So cool. Let's do another example that we saw already and just confirm for ourselves that this does indeed work. Maybe you're still skeptical that it works, and rightfully so. Let's say we're going from 0 to 2 and we're doing negative x plus 2. Okay. We know for a fact what this area should be, and we know it because, not because we used our calculator, but because we drew a picture. Negative x plus 2 has a y-intercept of 2. It also has an x-intercept of 2. So if I draw this line, it looks like this. This area is this triangle. The area of this triangle, you should notice, is 2, because the height is 2, the base is 2. 1/2 times 2 times 2 is just 2. Great. So let's integrate it. This integral becomes negative 1/2 x squared plus 2x, evaluated from 0 to 2. And so I'll just plug in 2. When I plug in 2, I get 2 squared, which is 4, times negative 1/2 is negative 2 plus 4. That's my f of b, my capital F of 2. And then I'll subtract f of 0, which is just 0, so I get 2, and that's awesome because that's the area of the triangle. Fantastic. Really exciting. I'm super excited. Hopefully you are too. I'm going to end this video with a bit of a tougher problem for us to figure out, but we can still do it. And I'm going to change variables here. I'm not going to use x anymore because x is boring. Let's say I have the integral from 0 to 4 of 1 minus the square root of r divided by the square root of r, dr. Okay. Yikes, this looks like a disaster. I look at this function, I have no idea how to find its antiderivative, but I do know how to do algebra. Almost every time you have a fraction with one term in the bottom and multiple terms on the top, we want to rip that fraction apart into separate fractions. Even when the bottom has more than one term, we will occasionally do this, but almost every time if the bottom just has one term, we will definitely do this. So this will become 1 over root r minus root r over root r dr. Oh, and this is super nice because this is just the integral from 0 to 4. Well, 1 over root r, see, root r is r to the 1/2 power, so this is r to the negative 1/2 power. Root r over root r, oh, that's just 1. Oh, that's great. Okay. And so what is this? Well, the antiderivative of this, I add 1 to the power, I divide by that new power. This becomes 2r to the 1/2 minus r. I'm going from 0 to 4. I plug in 4, I get 4 minus 4. I plug in 0, I get 0 minus 0. This is just 0. Super cool, right? And I'll leave us with one last thing here. One final example. Because I don't want us to forget things like this, okay? If I'm taking the integral, maybe from 0 to 3, and maybe my function is something like square root of 9 minus x squared. I don't know how to take this antiderivative. I just don't. I can't add 1 to the power and divide by the new power because this x squared messes that up, right? It makes a chain rule thing happen. I can't do that. So I sit here and I think to myself, well, what can I possibly do? If it's the case that you are given an integral and you have absolutely no idea what to do, I cannot emphasize enough that you draw a picture. Drawing a picture is so powerful because we remember, not only does this tell us the antiderivative, but it also tells us the area underneath this curve. The square root of 9 minus x squared is a nice half circle. If I'm going from 0 all the way up to 3, it's just a nice quarter circle. And I know the area of a quarter circle with radius 3, because the area of the whole circle is pi r squared, which is 9 pi. So the area of this quarter circle is 9 pi over 4. I cannot stress enough. Please, please, please don't lose the conceptual understanding of an integral once we start getting into all of this algebra and these nice formulas. We'll get other formulas just like it, but please do not forget that we can still conceptually do this. As the days go on, you're more and more and more going to be using algebra, but don't lose that understanding. And if you ever hit a roadblock, draw a picture 100% of the time. It helps so much. Great. So that's the fundamental theorem of calculus. It's awesome. I hope you enjoyed it as much as I did, and I will see you next time.